On February 8, 2026, Linus Torvalds made an announcement that marked the end of an era. Kernel version 6.19 would be the final release in the 6X series, and the next version would be called 7.0 for those following Linux development closely. This was not exactly a surprise, but it still carried a certain weight. The 6X series had been around for years, and saying goodbye to it felt like turning a page in computing history. But here is the thing that often confuses people outside the Linux world: when the kernel jumps from version 6 to version 7, it does not mean what you might think in most software. A major version bump signals some kind of fundamental change or break from the past. Not so with the Linux kernel. The major version number carries no intrinsic meaning at all. You could almost think of it as an arbitrary label. What matters is that the kernel maintains stable interfaces and consistent behavior even across these major version jumps. So why change the number at all? The answer goes back to how minor versions are handled. Since version 3X, the kernel team has capped minor versions around 20. The reasoning is actually quite practical. If you let minor version numbers climb too high, people start getting confused. They might assume that jumping from version 6.30 to 6.31 represents a smaller change than going from 6.1 to 6.2. That perception problem can create misunderstandings about what each release actually delivers. By resetting the major version periodically, the developers sidestep that confusion entirely. To understand why we have reached this point, it helps to look back at where it all began. Linus Torvalds created the Linux kernel in 1991. By December of that same year, version 0.11 made the kernel self-hosting, meaning it could compile itself. Then, in March 1994, version 1.00 arrived, containing over 170,000 lines of source code. From those early days to now, the version number has always been more about practicality than pageantry. The development process for Linux 7.0 follows the same well-established rhythm that kernel developers have used for years. Once the decision was made to bump the version number, the merge window swung open on February 9, 2026. This 2-week period is when maintainers submit their new features and major changes for inclusion in the upcoming release. It is a busy time, with code flowing in from all corners of the kernel ecosystem. Once that window closes, the focus shifts entirely to stabilization. The first release candidate, what developers call RC1, is expected around February 22, 2026. From their weekly release, candidates follow like clockwork. Each RC gives the broader community a chance to test the kernel on their hardware, report bugs, and help iron out any issues before the final version ships. It is a public testing phase that relies on thousands of eyes looking for problems. The final release date depends on how smoothly those weeks of testing go. If everything goes well, and 7 release candidates are enough, we can expect Linux 7.0 to land on April 12, 2026. If developers need an extra week of testing with an 8th release candidate, the release slips to April 19, 2026. Either way, we are looking at roughly a 2-month cycle from merge window to final release. That timeline has become the standard cadence for kernel development, and 7.0 follows it faithfully. The flagship desktop feature in Linux 7.0 is something called the tip time slice extension, and it addresses a problem that has frustrated users for years when you are running demanding applications like games or audio production software. The kernel scheduler normally interrupts processes on a fixed schedule. This preemption works fine for most workloads, but it becomes problematic when An application is right in the middle of something critical. Imagine a game rendering a complex frame, only to have the scheduler yank away its CPU time at the worst possible moment. The result is a stutter or frame drop that players definitely notice. The tip mechanism solves this elegantly. Applications can now request a temporary time extension from the scheduler when they are performing critical work. Think of it like a student asking for a few extra minutes to finish an exam question. The scheduler receives the request, and if it approves, lets the application keep running past its normal time slice. This prevents those jarring interruptions at inopportune moments for gamers. This could translate to improved 1% low frame rates, which is the metric that really matters for smooth gameplay. Those minimum frame rates are what determine whether a game feels fluid or stuttery during intense scenes. There is another improvement worth mentioning here. Linux 7.0 introduces something called the sheaves memory handling mechanism. While this was originally designed with servers in mind, it turns out to benefit desktop users as well. Many CPU-heavy applications spend a lot of time constantly allocating and releasing memory. Games are notorious for this behavior. Sheaves optimizes how the kernel handles these allocation patterns, which reduces latency spikes when the processor is under heavy load. The combined effect of tip and sheaves should make Linux noticeably snappier when running heavyweight applications, whether that is a modern game pushing your hardware or professional software handling complex workloads. These are exactly the kinds of improvements that everyday users will actually feel, rather than just seeing bigger numbers in benchmarks. For anyone running servers or managing container infrastructure, Linux 7.0 brings some genuinely practical improvements. The standout feature here is something called the Open Tree namespace, and it addresses a bottleneck that has frustrated infrastructure teams for quite a while when you are spinning up containers in Docker or Kubernetes environments. There is a lot of overhead involved in setting up the namespace isolation that keeps everything secure and separated. The Open Tree namespace dramatically speeds up this process, which matters enormously for microservices architectures, where containers are constantly being created and destroyed. If you are running a platform that needs to scale up quickly in response to traffic spikes, this can make a real difference. Network performance gets serious attention in this release, too. The improvements to EO-Uring and zero-copy networking target environments, handling substantial network traffic, think 10 gigabits per second and beyond. Traditionally, moving that much data through the kernel meant significant CPU overhead as data got copied between kernel space and user space. Zero-copy techniques eliminate much of that redundant work. Your CPUs spend less time shuffling data around and more time doing actual useful computation for hosting providers and cloud platforms. This translates directly into better efficiency and the ability to handle more traffic with the same hardware. The scheduler has also received tuning specifically aimed at server workloads. Web servers and database servers have different performance characteristics than desktop applications or gaming workloads. They handle many concurrent connections and need consistent response times under load. The optimizations in 7.0 help these services manage load more smoothly, reducing latency spikes that users might otherwise notice. Taken together, these changes make this release particularly significant for enterprise deployments and anyone running production infrastructure. One of the biggest technical milestones in Linux 7.0 is something that developers have been working toward for years. Rust support is now officially stable in the kernel, graduating from its previous experimental status. This is a significant shift because it means writing kernel code in a memory-safe language is no longer just a proof of concept. Drivers and other components can now be built in Rust with full upstream support, which should lead to fewer memory-related bugs and security vulnerabilities over time. On the ARM side of things, there is a new feature that might sound obscure, but has real performance implications. The kernel now supports atomic 64-byte loads on ARM processors. This allows the processor to load a full cache line atomically, which reduces the overhead of certain operations that previously required more complex synchronization. It is the kind of low-level improvement that adds up in high-performance workloads. The I/O Uring subsystem also received some attention. A change to non-circular SQ entries means that submission queue entries called SQs can now stay hot in cache more effectively. This reduces cache misses and improves efficiency for applications that rely heavily on asynchronous I/O. BTRFS users have several reasons to be happy. Direct I/O support now works when using block sizes larger than the page size, which removes a previous limitation that could force workarounds. There is also a new remap tree feature, which acts as a translation layer for logical block addresses. This enables certain changes to happen without moving or rewriting the actual blocks, making copy on write operations more efficient. It is a clever piece of engineering that should reduce write amplification and improve performance for snapshot-heavy workloads. And finally, a small but fun change: you can now customize the Tux boot logo. It is a minor touch, but it speaks to the community-driven nature of the project. Now, when it comes to actually getting Linux 7.0 on your system, the timeline varies quite a bit depending on which distribution you use. If you are someone who likes living on the bleeding edge, rolling release distributions will be your first stop. OpenSUSE, Tumbleweed, and Arch Linux typically pick up new kernel versions within just a few weeks of the official release. These distributions serve as excellent testing grounds because their users expect frequent updates and are generally comfortable troubleshooting issues. The feedback from these communities helps identify bugs before the kernel makes its way into more stable releases for users who prefer stability over the latest features. The wait will be longer. Canonical is aiming to ship Linux 7.0 with Ubuntu 26. LTS scheduled for release in April 2026. Fedora 44 is targeting a similar time frame. These releases prioritize reliability and extensive testing, which means they will not include the new kernel until it has been thoroughly validated. Gaming focused distributions have their own schedules to consider. Bazite, which is derived from Fedora, moves relatively quickly and expects to adopt the new kernel by May 2026. Chimerouse, designed specifically for handheld gaming devices, is targeting June of that same year. These timelines make sense given the gaming community's particular interest in the performance improvements that 7.0 brings. It is worth understanding how this all fits together with long-term support kernels. Kernel 6.12, for instance, is an LTS release that will be supported all the way through 2035. That sounds like an eternity in technology terms, but it serves a crucial purpose. Enterprise systems, embedded devices, and critical infrastructure often cannot afford the risk of frequent kernel upgrades. They need a stable foundation that receives security patches and bug fixes for years. Meanwhile, desktop users and gaming enthusiasts can chase the cutting edge with newer kernels. The Linux ecosystem accommodates both approaches simultaneously, and that flexibility is one of its greatest strengths.